Hi, so today we're going to look at lesson 5.1 on extrema on an interval and lesson 5.4 on concavity and the second derivative test. Let's start with the basics in 5.1. So we already know that graphs can contain minimum and maximum values as shown here. Here are minimum and maximum values. This is a maximum, this is a min. Absolute maxes and mins are at the highest and lowest points on the graph. So for example, this point is an absolute max, and there's no absolute minimum because this graph just continues on forever in the negative land. And also this is a relative min, and this is a relative max. Any hills and valleys in between are known as relative extrema. We also have to note that extreme values can only occur if the function of some c value exists. Relative extrema can occur in two ways, with a smooth curve, here's a smooth curve, or a sharp point. And you just have to note that with a sharp point, the derivative cannot exist at the point because you can draw it in multiple angles, so the derivative does not exist at this point. Also, if this graph had endpoints, say right here and here, these cannot be referred to as local maxes and mins. So if we're given a function, the first step is to find the derivative. So here's a function. F of x is equal to x cubed minus 12x plus 2. And here's the derivative. And then you can simplify this further. It's supposed to be a 4 right here. All right. And then you can see that you get critical numbers of x equals 2 and x equals negative 2. From there, we can plug in these points to the derivative and then we'll get 0. This is telling us that these x values are critical numbers. So we can say that relative extrema only occur at critical points, but critical points do not necessarily have to occur on relative maximum or minimum values. It is just where the derivative is undefined or equal to 0. So that you can see that right here. So say we still had this graph right here. This point right here the derivative here is 0, obviously because it's straight, but it is not a relative value because it's not a hill or a valley. If you wanted to get the absolute extrema of this function, we would still get the derivative of the given function, which is 3x squared minus 6x, which is 3x minus 2. But then we have to set this equal to 0 and then solve for x. Then all we would have to do is plug in the critical numbers, and the critical numbers you get as a result into the original function, also including the x values on the closed interval, and then we would get your absolute extreme values. So say this is our critical numbers that we get. And then when you plug this in to the original function, we get 0 and negative 4. Say we are given a problem like this. If we wanted to locate the absolute extrema on an interval, we would still get the derivative of the function. So say this is the function. And then the derivative. But then we have to set this equal to 0 and then solve for x so we get the critical numbers. The critical numbers we get are x is equal to 0 and 2. From here, we have to plug these into the original equation. We also have to plug in each x value from the beginning to the end of the interval. And then from here we can see that we get our absolute maxes and absolute min values. When we plug in 4, we get 16. Absolute minimum, get 2, negative 4. Okay, this was the basics for 5.1, and we're going to now look at 5.4. Okay, so now we're going to discuss how this applies to lesson 5.4 with concavity and the second derivative test. The second derivative test helps you classify relative extreme values by using the sign of the second derivative at the critical number. And this could either be positive or negative. To use this test, it is first necessary to understand the concept of concavity. So if a curve is concave upward, we will know that the graph of f lies above the tangent lines. Like this. Here's a tangent line. Here's another tangent line. Whereas a concave downward graph, like this, is below all of the tangent lines. We see here that the graph of f is above these tangent lines, and with a downward curve, the graph of f lies below these tangent lines. To test for concavity, we have to take the second derivative of the function and plug in the x values that we are testing. And if it's positive, it's concave upward, and if it's negative, it's concave downward. If it's equal to 0, that means that there is no concavity, or it's an inflection point. So, I am going to make a graph. So we have to get the critical numbers for the second derivative. The critical numbers are x is equal to 1. And we know that this is a point of inflection because it is a critical number of the second derivative test. As I said before, we have to plug in numbers bigger and smaller than 1 to test the concavity. So first, this is going to be smaller than 1, which is a negative 6. And then if we test 1, it's 0, point of inflection. And then if we test a number bigger than 1, so 2, we get a positive 6. And if we insert this in our graph, we can now see that we get a negative number when we plug in 0, so that means that it's concave down. And then this leaves us with a relative max with the point 0, negative 2. And we get the y value by plugging the x value back into the original function. If we were to test 1, it is 0. And this cannot be determined with the second derivative test, so this means you have to go back to the first. And then when we plug in a number bigger than 1, we get a positive number, which means that this is concave up. So we get a relative min of 2, negative 4. And again, this y value comes from plugging 2 back into the original function. Back to points of inflection. These are points where the concavity of the graph changes. To test for an inflection point, if we go back to an example, we can see here that if we plug in 1 in the second derivative, the answer was 0. Remember that a point of inflection is a point, as it says in its name. It is not just a number. So that means that 0 cannot be your answer. It would have to be 1, 0 is your point of inflection. So now we are wondering why and when we would use the second derivative test. Why? To determine whether a critical point is a relative min or max in the graph. When? If we need to find any critical points, extreme values, or a concavity on the graph. I hope this tutorial was helpful and thank you for watching.